Deep learning answers that question through layered neural networks, optimization, and representation learning. How do modern systems learn patterns from images, language, and other complex data? You will move from core principles to architectures, training methods, evaluation, scalability, and generative models. This unit aims to build a deep understanding of fundamental concepts and advanced methodologies in deep learning. It connects theory with practical applications across computer vision, natural language processing, and graph-based tasks. It also prepares you to evaluate approaches, understand limitations, and apply methods to real-world problems. Deep learning is a subset of artificial intelligence and machine learning. It focuses on training neural networks with multiple layers to learn and extract hierarchical patterns from large amounts of data. Its scope includes image recognition, speech processing, autonomous systems, and generative artificial intelligence such as text generation and image synthesis. The development of neural networks moved through several turning points. McCulloch and Pitts introduced artificial neurons, Rosenblatt presented the perceptron, and backpropagation was reintroduced by Rumelhart and Hinton. Later, deep belief networks renewed interest, and AlexNet marked a major turning point in deep learning research. Deep learning is important because it automates feature extraction, improves accuracy, and scales with advanced hardware. Learning paradigms describe how models are trained on data. The two primary paradigms here are supervised learning and unsupervised learning. They differ in the kind of data they use, the goals they pursue, the techniques they apply, and the challenges they create during model development and evaluation. Supervised learning trains a model on labeled data where each input has a corresponding output. It is used for classification and regression tasks. Examples in the material include predicting housing prices, spam detection in emails, medical diagnosis, and stock price prediction. Unsupervised learning looks for patterns in unlabeled data without predefined outputs. Its fundamental techniques include clustering and dimensionality reduction, such as principal component analysis for visualization. Use cases include customer segmentation, market basket analysis, anomaly detection, and image compression. But evaluation is harder because there is no ground truth. Regularization methods, such as L1 and L2 penalties, along with dropout and cross-validation, help balance complexity and generalization. A central theory is that neural networks are universal function approximators. A feed-forward network with at least one hidden layer and enough neurons can approximate any continuous function on a closed and bounded subset. Core components are the input layer, hidden layers, output layer, and nonlinear activation functions. Input-output activations. Deep learning models are trained to minimize a loss function that measures the gap between predicted and true values. Examples given here are mean squared error and cross-entropy loss. Gradient descent updates model weights iteratively using the gradient of that loss, with variants such as stochastic gradient descent, atom, RMSprop, and momentum, 0203, 0405. Backpropagation computes gradients efficiently by applying the chain rule and sending errors backward through the network. Representation learning then allows models to discover features directly from raw data. In deep networks, lower layers can capture basic features like edges, while higher layers capture more complex patterns such as object shapes. Regularization aims to prevent overfitting, especially when a model fits training data well but struggles on unseen data. The material highlights L1 and L2 regularization, dropout, and batch normalization. These methods add penalties, deactivate neurons during training, or normalize layer inputs to stabilize learning and improve generalization. Different deep architectures suit different kinds of tasks. Feed-forward neural networks provide a basic structure for supervised learning. Convolutional neural networks are specialized for image data. Recurrent neural networks handle sequential data such as time series and text, and transformers use self-attention to capture contextual relationships in natural language processing. Deep learning often optimizes highly non-convex loss landscapes, with many local minima and saddle points. Modern algorithms may not find a global minimum, yet they can still converge to minima that generalize well. Performance is then measured with task-specific metrics for classification, regression, and generative modeling. Linear algebra explains transformations, matrix operations, and tensor manipulations. Probability and statistics support probabilistic models, loss functions, and uncertainty quantification. While information theory shapes ideas such as entropy and mutual information, and numerical methods support gradient computation and optimization. Scalability depends on hardware acceleration and distributed learning. Graphics processing units and tensor processing units support parallel computation, while data parallelism and model parallelism make training on massive data sets possible. Ethical concerns include bias in training data, transparency and explainability of predictions, and adverse societal impacts of artificial intelligence decisions. Its major limitation is that it cannot solve non-linearly separable problems like XOR. Deep networks learn hierarchical and non-linear representations. Their strengths include expressive power, feature learning, and scalability, but training can face vanishing gradients, exploding gradients, local minima, and overfitting. Increasing depth can improve expressive power and raise performance in tasks such as image classification and natural language processing. At the same time, deeper models are harder to optimize and demand more resources and time. Solutions named here include rectified linear unit activations, batch normalization, gradient clipping, dropout, and weight decay. Generative models learn to generate new data points similar to training data by estimating a dataset probability distribution. The material separates them into explicit density models and implicit density models. Variational autoencoders and diffusion models are explicit, while generative adversarial networks are implicit and generate samples without explicit distribution modeling. Diffusion models reverse a gradual noise adding process and produce highly realistic results, though they are computationally intensive.